Welcome to this video where we'll be looking at section 3.1.2. We'll be looking at indefinite integrals. All right, let's start right away with the definition of indefinite integrals. The indefinite integral of f of x is an expression which contains all antiderivatives of f of x. In the last video, we saw the definition of antiderivatives, and we also saw that a function has many different antiderivatives. So I don't like asking somebody to find an antiderivative because every single person could come up with a different answer. But really what we saw in proposition 3.1.1 is that any of these answers would be a constant away from my answer. So here's how we're going to kind of save that question. Instead of asking for one antiderivative, we'll ask for all antiderivative. So what your answer is going to look like is you're going to put g of x, which is your chosen antiderivative, and to make sure that your answer matches mine, you're going to add a plus c. And that plus c is just, it's not one specific constant, it represents all constant. All right, so this is a arbitrary constant. And so now you've written not one antiderivative, but all of them. All right, so let me show you what everything is. This symbol here is the symbol for integral. It's a big curly S. S stands for sum. We'll see why when we start talking about Riemann sums. The dx here is the same dx as df over dx. So it will represent a small change in x. All right, and the only part I haven't told you about is g of x. Well, I told you I didn't write it down. Let's write it down, where g of x is any antiderivative for f of x. So any function whose derivative is f. You just need to come up with one. You come up with one function g whose antiderivative, one function g who is an antiderivative, and a function g whose derivative is f, and that's what you put here. And then you add plus c to make sure that you represent all of them. All right, so let's try a few examples. All right, I'm asked for the integral of x cubed. So I need to find some antiderivative So I need to come up with a function whose derivative is x cubed. So I'm going to write x to the 4, but of course we're going to have to do, I don't know if you remember, let's go back. When we were looking to find an antiderivative for x5, just x6 wasn't good enough because we got an extra 6 in front, so we had to divide by 6. The same thing's going to happen here. If I want, sorry, it went too far. If I want just x cubed, x4 will not be good enough. I'm going to put a 1/4 in front. And so you could also write it this way, x to the 4 over 4 plus c. And to check that your answer is valid, all you have to do is take the derivative of your answer. You could do it with the plus c, since plus c is not going to change the derivative, but you don't need to. It's only g that is any antiderivative. So I'm going to take the derivative. I'm sorry, I forgot to lower the power by 1. So it's 4x cubed, and the 4's will cancel, so I get x cubed. If you take the derivative of this function, you need to get the one that's inside the integral sign. Oh yeah, and just by the way, I'm not going to use this much, but I'm going to use it at least once or twice. So this is called the integrand. The function that you're integrating is called the integrand. All right, let's do another one. I'm asked for the integral of 1 over 1 plus x squared. That means I need to find a function whose derivative is 1 over 1 plus x squared. Well, we have one in our tool bag of function. We have arctan, and so the answer is going to be arctan of x, as this function has the correct derivative. All right, so there's one case that I want to do separately because it's a tiny bit different than what you would expect. So let's look at this proposition, proposition 3.1.2. The definite integral of 1 over x is, well, you need an antiderivative. So you're thinking, well, I know ln of x would work. So ln of x plus c. That's okay, but it's not the best possible answer. To get the best one, I'm going to put absolute values here. All right, so because of these absolute value, I really want to show this to you separately. All right, so let's prove this. Remember, all we have to prove is that the derivative of this is 1 over x. So I'm going to try it. All right, so let's look at the derivative of just ln of x. So that gives you 1 over x. So g of x equals ln of x is an antiderivative. All right, let me sketch it. I have my first antiderivative right here. Now let me try a second one. What if I have log of minus x? All right, so this one's a bit different. I'm not going to be able to plug in positive number in it because then I get log of a negative number. So my x's will be negative. In fact, if you want to graph it, it's going to be the mirror image of the log of x. All right, I claim that that's another antiderivative. Let's check. If I take the derivative, I get 1 over minus x. And because of the chain rule, I'm going to multiply by the derivative of the interior. My interior is a bit more complicated than what I had here, so I need to differentiate it. So this is a chain rule. Now I get minus 1 over minus x. I get 1 over x. So log of minus x, that would give you a second antiderivative. All right, so I have one antiderivative that's valid for positive number and one that's valid for negative number. My original function is valid everywhere but 0. And so I would like my antiderivative to be valid on the same domain. And so what I'll do is I'll take the orange and I'll take the blue. If I put them together, I'll get log of absolute value of x. All right, it's going to first turn your number positive and then plug it in. So that's the best because it has the same domain as your original function. So it's g of x equals log of absolute value of x. And so that's what we'll put as the integral of 1 over x, log of absolute value of x. All right, so now we're ready to list all of the functions that we can integrate quickly, all of the functions for which we have an antiderivative already in our bag. All right, so here's a table of basic integrals. Those are the ones that you'll be able to do without, maybe not without thinking, but without writing an explanation. All right, so let's x to the n, we said that's x to the n plus 1, but you divide by n plus 1. Right, just like here we had x to the 4 over 4. We have x to the 4 over 4. In general, we'll increase the power by 1 and divide by that. And that's going to be valid as long as n is not minus 1, because otherwise I'm dividing by 0, and that's no good. When n is equal to minus 1, the function is really 1 over x. And then we just saw in the last proposition that the best answer for this is log of absolute value of x. All right, if I have e to the x, I'm looking for a function whose derivative is e to the x. We have e to the x. That's good. That works. A to the x, let me give it to you. That one's not obvious, but you will need it once in a while. It's a to the x divided by log of a. So just like when you take the derivative of a to the x, you get an extra ln of a on top. To cancel it, you divide by it first. All right, plus c. The integral of sine, I need a function whose derivative is sine. Cosine would get an extra minus, so I'm going to put a minus in front. But this one, don't need to adjust it. The derivative of sine is exactly cosine, so the integral of cosine is exactly sine. So it's backwards from derivative. It's the integral of sine that has the minus here. All right, so now the derivative of tan is secant squared. So if I try to integrate secant squared, I'm going to get tan of x plus c. If I try to integrate secant x tan x, I'm going to get secant x. So whenever we have a derivative that we know, we have an integral that we know. We know the derivative of tan is secant squared, so we know the integral of secant squared is tan. All right, cotan, that derivative is cosecant squared with a minus, but I put a minus on that side because it looks nicer. And then this one is cosecant x cotan of x. All right, so I put them in this order because to go from here to here, you just add co. So here I have sine, here I have cosine. Here I have secant squared, here I have cosecant squared. Here I have secant tan, cosecant cotan. All right, so when you add that co, all you have to do is add a minus and put cos in front of everything. So instead of tan, it's minus cotan. That's how I remember it. All right, final two. The integral of 1 over a squared plus x squared, that's going to be 1 over a arctan of x over a. This one, we proved it for a equals 3, I think, in worksheet 1, the last problem. I think it's problem 8. All right, and similarly, you have a formula like this for arcsine. We know it for a equals 1, and the same proof that gave you this in worksheet 1 will give you this one for square root of a squared minus 1 minus x squared. So if you have an a squared instead of a 1, you just have to divide by a here. All right, so let's try 2. Let's try this one. I claim that you can find the integral of cube root of x using one of these. Do you see it? When you took derivatives of roots, you tended to write them as powers and then use the power rule. We'll do the same thing. I'm going to use this rule with n equals a third. So I'll get a third plus 1 over a third plus 1. So I'll get x to the fourth. Oh, sorry. I made a really common mistake. I forgot to put the plus c. That's going to cost you a tiny bit, but you're going to have a minor deduction if you forget the plus c, so try to remember. So here I'll get 4/3 when I add the fractions and 4/3, and if you want, you could write it as 3/4 x to the 4/3. Remember, when we bring a fraction to the top, you switch, you flip it. All right, so we computed our integral. It's 3/4 x to the 4/3. All right, let's try this one. We have the integral of x squared plus 9. It looks a lot like this one. I mean, the order is flipped. That doesn't matter much. What you need to do, though, is you need to figure out what a is. So we have a squared is 9. And so a, I'm going to take the positive root because of this. So a is 3. So I'm going to get the integral of 3 squared plus x squared 1. That's 1 over 3 arctan of x over 3 plus c. Oh, I forgot my plus c here. Sorry, I was low on space. So make sure you put a plus c here and here. All right, so at this point, we can integrate a good list of functions but not that many, right? As soon as I divert a bit from this list, we don't know what to do. So what we'll do in the next video, we'll look at basic rules of integration. So just like for derivatives, we needed to have rules that told us how to mix different functions together and still be able to compute its derivative. We'll have the same for integrals, right? So we'll start that in the next video.